All right, good morning, everyone. Today we're going to continue with the theme of making sure we know what type of hypothesis tests that we are doing. So from yesterday, I've created this table to synthesize what we need for every type of test. So looking at this table here, we have every test listed. So if I counted correctly, there are 9 tests that we have done this year, and that's all that we're going to do. So we have our 1 sample proportion, 2 sample proportion, 1 sample mean, 2 sample mean, a paired t-test, the chi-square goodness of fit, the chi-square homogeneity, the chi-square test for independence, and then the slope regression test. So looking at this, this is a great way to know what type of test that you're given. So we have the actual values that are given to you, and then some key terms that you might want to look for in the problem. So looking at the proportion tests, so these two are kind of similar to each other, except that we have one proportion, or excuse me, 1 sample size versus 2 sample sizes. And so here, if we want to know, do we have a proportion test? Well, are they given? Is a proportion given? Is there a percentage? Does it say we took a sample of 100 and found that 40 of them do whatever? So that would also be a proportion. So 40 over 100 would be our p hat. And then similarly, we need the same thing for a 2 sample proportion. However, we have 2 samples rather than just 1. For our mean tests, this is if we're looking at if we're given a mean or a standard deviation. This is really a big one here for the mean test. Are you given a standard deviation? Because if you are, then that pretty much guarantees that this is some type of t-test, whether that's 1 sample, 2 sample, or a paired t. And then specifically for the paired t-test, a lot of times we're looking at a sort of before and after situation in terms of, we took a sample of people, we tested their blood pressure, and then we made them run a mile and then measured their blood pressure again. Something like that. So there's a lot of before and after situations going on, because a paired t-test is really like the matched pair design during experiments, where if we had that sort of before and after situation going on, we knew that that was a matched pair design. Similar, we have a matched or paired t-test, sometimes also noted as a matched pair t-test. And then we can dive into our chi-square tests, the ones that we've been focusing on the last week. And this one here, we really need to see, are we looking at these observed and expected values? So these ones are kind of the key giveaway that this is going to be a chi-square test. Specifically for the goodness fit, we're looking at equality, if there are percentages for different categories given, and then there's only 1 row or column of observed values. And then for homogeneity, is there some sort of similarity going on? Do we have a 2-way table here? And then actually, there is an error here. Relationship should go for independence, not homogeneity. So if in a moment, I'm going to give you time to pause the video and copy this table down, but relationship should go with independence. So for independence, if it explicitly says independent, are they associated? Is there a relationship going on? That is our independence. And then lastly, for the slope regression, the one that we talked about yesterday, this one, is there an output table given to you in terms of slope and regression? Do we have a slope? Do we have the standard error? Or maybe sometimes they'll give you a list of data points. So this is something that we haven't dealt with necessarily, but if they were to give you, an X and Y table, then you could put that in your calculator and run the the two variable summary and get your slope and standard error. And we'll look at a problem like that next week so that we are all comfortable doing that in our calculator. I know we did it in Unit 2, but just as a review, a refresh on that, we will take a look at that next week. But this is kind of our guide for the next couple days in terms of review, because I know that there are a lot of significance tests. There are 9 in total, and we really need to focus on, how do we know when we are supposed to do a one sample mean versus a paired t-test, or that kind of thing. So we're going to focus on that today, and then we'll dive deeper into this again tomorrow. So let's pause the video now, give you a chance to write down this table of values and keywords. And please note again, make sure that the relationship key term goes down for independence. So please just take 5 minutes on your own to copy down this problem or this table, and I will give you, and then we'll come back together for the example. So I'll give you 5 minutes now. Please pause the video and then go ahead and do example, and then we'll come back for example number 1. All right, welcome back. Hopefully you had a chance to write everything down. Let's go ahead and dive into example number 1. So an e-commerce research company claims that 60% or more of graduate students have bought merchandise online. A consumer group is suspicious of the claim and thinks the proportion is lower than 60%. So a random sample of 80 graduate students show that only 22 students have ever done so. Is there enough evidence to show that the true proportion is lower than 60%? Okay, so let's use this table of information above to narrow down what type of hypothesis test we're going to do. So the biggest thing that's jumping out at me right now is that they give me this value of 60%. So that is something that's really jumping out at me. I know that if I'm given a percentage, most likely it's going to be a proportion test. But let's keep reading to make sure. So they say they took a sample of 80 graduate students and they found that only 22 of them have ever purchased something online. Well, again, if I go back up to my table, I see where it says took a sample of and found that some number of them did something. So this to me is jumping out as a proportion. So we need to figure out, are we looking at a 1 sample Z or a 2 sample Z? Well, I only see here that they took a random sample of 80 grad students. So I don't see anywhere in the problem where they say they took another sample of 100 grad students or 50 or anything like that. So this is going to be a 1 sample Z test. So let's go ahead and just extract what we're given. So since 60% is the total claim, that's going to be our P. They said they took a sample of 80, so N is 80. Then P hat is going to be this proportion. They found 22 of the 80. So let's go ahead and convert that to a decimal here. So 0.275. Let's convert this to a decimal as well. 0.60. And so our hypotheses here are going to be, our null is that P is equal to 60%. Our alternates, so they said that we wanted to see if the true proportion is lower. So they want to see, is our P going to be less than 60%? And now we need to do our conditions. So our second step is the conditions. So RIN or NER, whichever section you are in, our acronym for that. So random, they said they took a random sample, so we're good there. Independent, well, that's going to be our n over the population. So 80 over, let's say they have, there's a ton of grad students, so we know that this is going to be less than 10%. So we're good there. And then lastly, our normal condition, since this is a proportion, I know that I need to do my n times p, and that has to be greater than 10, and my n times 1 minus p also has to be greater than 10. So here, my p is 60%, so let's extend this over here. So I have n is 80, then 0.6. Let's make sure that's clear that that is a decimal. And then we have 80 times 1 minus 0.06. And so if I crunch that out, I will find that 0.6 times 80 is 48. So that's definitely greater than 10. And then 80 times 0.4 is 32, which is also greater than 10. So we've met the normal condition here. So now I can go ahead and calculate my test statistic. So step 3 here, we have z is equal to our statistic, so our p hat, 0.275, minus our parameter, 0.6, all over. And then again, in my denominator, I need to be very clear here. This is where we use our p, not p hat. If we have p, we should use it. So the denominator needs to be 0.6 times 1 minus 0.6 over 80. And then that's going to give me negative 5.93. And if I look on my z-table, I can see that I only go up to negative 3.9. So I'm not going to have negative 5 on here. But if I visualize my normal distribution, I know since this is a negative z-score, I'm going to be all the way over here. And so I'm going to be at practically 0 for my percentage. So that is what our percentage is going to be here. So the percent of z equals 0.593 is equal to 0. Now I need to make sure, am I done? Is this my p-value? Well, let's go back to our alternate hypothesis, and I see that we are less than, so I don't need to do anything. So my p-value is going to be equal to 0 here. And so then that's definitely going to be less than alpha. So we're going to reject our null hypothesis. So since we reject the null, then our final statement here is going to be there is enough evidence to show, well, let's include our alpha level here. There's enough evidence at the, well, an alpha is not given, but we can say 0.05 level to show that the true proportion is lower than 60%. So that was our alternate hypothesis. So that is what we are trying to conclude here. So that is our final conclusion. All right, so using this chart that we've created, go ahead and complete the classwork. So that is going to be on Google Forms. So please log into Google Classroom, follow that link, and then submit your answers. And then if you have questions, I will be on Zoom at 8:20. All right, have a great rest of your day, everyone.